we're talking integrated design, but in a lot of ways, these three presentations are integrated from that theme of build tight, ventilate right, and all the things that flow out of that. Integrated design is going to be part of the way that you actually achieve the design results in a high performance home. I know that a number of pieces that Rob will be talking about in this in terms of right sizing mechanicals with high performance, and that becomes really critical, especially when you get to step 3 and beyond, just because of the advantages that are in terms of matching it up properly, but also in terms of best practices and next practices that you need to be aware of. And I won't steal any thunder from Rob there, so take it away.
Okay. Hi, everyone. Thanks for attending. Today, I'd like to talk about standards of practice, the way we have been doing HVAC and mechanical systems, the way we should be doing them, and the way we will be required to do them in the future. I'm going to spend time on the profound importance of proper load calculations and how that impacts everything else about HVAC mechanical systems. I'll talk a bit about air-to-water heat pumps, an emerging technology that we are all going to have to understand to align with code changes that are here now and in Vancouver and are coming throughout BC. And finally, I'll review the key takeaways. How do we approach HVAC systems now? Typically, a home is designed and ready to be built or is in the process of being built. Then a heating contractor will be asked to provide a quote. The heating contractor will provide a quote and a system proposal based on 1, a rule of thumb, guess about the sizing requirements, a standardized approach, including preferred equipment, and 3, assumptions about routing and sizing of ducting, grills, registers, and everything else. The quote will rarely include any details about routing, sizing, quality assurance, commissioning, etc. And either a favorite contractor or a lowest quote gets the job. The HVAC is either shoehorned into the building as was priced, or it's modified with change order extras after it's too late to do any meaningful coordination. We might get lucky and there's no problems, in other words, coincidence, but more often the system is oversized, costs more than it needed to install, used bigger ducting than was necessary, is going to short cycle, costs more to operate, and not last as long. In addition to all that, it's probably going to be noisier and more uncomfortable than it could have been. So how do we resolve the issues of current practices? Do it with best practices. Before building permit, engage a designer or a competent contractor. And I'd suggest if you're going to do your design with a contractor, it's best to hire the contractor for the design portion only with no commitment to the installation contract. Proper load calculations to CSA F28012 method, no other. Without this, everything else is a crapshoot. Get them to coordinate with the design team. For example, a homeowner, architect or home designer, a builder, structural engineer. Included in this process would be clarifying client expectations, provide system options, addressing duct routing issues and installation obstacles. Get them to provide a design that everyone is happy with. Get them to install as designed. And if the designer and the installing contractor are not the same, get the designer to inspect the installation to ensure it meets the design intent at an acceptable standard of practice. And finally, get them to commission the system properly and thoroughly before occupancy. Next, practices. Governments at every level are changing the way we practice HVAC. Codes, decarbonization, electrification, and they're doing it with regulations and incentives. The market is trending toward higher performance. and higher expectations for performance and comfort. The technologies are adapting and evolving rapidly. There are a variety of approaches to heating, cooling, and ventilation, which are increasing as more and more products enter the market. Therefore, as an industry, we need to adapt and evolve as well. This means more and better training. Governments will need to adopt best practices as a compliance requirement, which means establishing a standard and enforcing it. Load calculations and system designs upfront before building permit, installation inspections, and blower door tests before cover-up, and commissioning verification before occupancy. And all this harmonized so that the rules are the same from one authority having jurisdiction to the next, which is not the case now. From one city to another, the rules are different. CSA F28012 is just the accepted method of applying the math and physics to determine how much heat loss and heat gain will occur in any given building. It's the most current and most accurate methodology, and it's required by code, although not yet strictly enforced in most jurisdictions in BC. Throughout Canada and the US, there have been multiple independent studies that have confirmed what many of us already knew, that far too many systems are grossly oversized. This means equipment gets bigger, ducting is bigger, budgets are bigger, operating costs are higher, life cycle of equipment is shorter, comfort is compromised, and the risk of liability goes up. As stated, CSA F28012 is a method of using math and physics to figure out. The method has been acquired by various private companies and industry organizations and put into their own. If you're a full-time designer, you would probably use the more expensive and sophisticated software. If you're a contractor in BC, you probably want to use the software created by TECA, T-E-C-A, the industry organization that represents heating contractors. It's not expensive, it's well supported by the industry organization, it has much less of a learning curve. In fact, the TECA load calculations are probably what you will see the most. There's also HOT 2000. It's in a category of its own though. This program was developed for the sole purpose of calculating the energy use of a home. It's the exclusive program used by energy advisors to model buildings. This is not a program that provides load calculations in the kind of detail that informs a proper HVAC design. The calculations that an energy advisor provides and the calculations that HVAC designer provides are two different things. It's important to remember that. So a while ago, EcoLighten had the privilege of providing some studies for Enercan as part of their LEAP project. We provided comparisons of load calculations for various programs for houses throughout the whole province. North Shore and one in Chilliwack. Each of them had been provided with HVAC quotes before we did any calculations. And here's the results. As you can see, the oversizing of the heating system was substantial. Two of them about 100% oversized, and one 50% oversized on the heating side. Two of them more than 50% oversized on the cooling side, and one less than half the size it needed to be. These are only three of the examples of what we saw. Proper diligence is ignored, and load calculations are replaced by rule of thumb. The slide shows you a list of information a designer will need to perform the calculations. You'll see it's very similar to what an energy advisor plans. They need to plan. Establish an infiltration target. Established for you by compliance requirements in some jurisdictions like Vancouver, which is currently 3.5, and anywhere that requires a step code. Sometimes the plan submitted for building permit will evolve. That's normal. But if you know ahead of time what you want to ultimately build, it's critical that this information is given to your HVAC designer. For example, if you have a plan, at post-occupancy, one room is going to turn into a different kind of use, it's best that your designer knows ahead of time. And finally, if you have already established what is not negotiable as far as systems go, it's important to make it clear. For example, radiant versus forced air, geothermal versus air-to-water heat pump, cooling or no cooling, etc. Sometimes clients already have their minds made up, and it's not worth the effort to try and convince them of other options. Load calculations are owed to you. You own them. So this should create the expectation that they are going to be done and going to be done properly. And they are going to be delivered to you for your review. There's a lot of pages of numbers, but all you need to know are a few things to review. First of all, check to make sure the area of the house you're building and the area of the house on the calculation results don't vary more than 3 or 4%. If it's more than that, it usually means there's an error input somewhere. If a Hot 2000 energy model has been done, check that the loads are within a 10% variance. If the Hot 2000 says the peak load condition for the house for heating, for example, is say 50,000 BTUs, then your F280 12 load calculations should be close to 50,000 BTUs within 10%. Review the assembly details to ensure that they're the same on the calculations as they are on the plans, that there wasn't any miscommunications. And make sure the design conditions, such as the outdoor and indoor winter and summer temperatures, are reasonable for your location and are in the correct climate zone. Most of these programs will give some analysis in the form of which parts of the building are contributing more or less to the heat loss and gain. This is an effective tool to understand the impact, optional upgrades, or cost-saving approaches to the building. Remember, you own the load calculations, so you can use them. Air-to-water heat pumps. A heat pump moves heat from one place to another. Using refrigerant and compression, it will absorb heat from one place and reject it to another. The most conventional heat pump that's been around for many decades is an air-to-air heat pump. In the winter, it absorbs heat from the outside air and rejects it to the air inside the house, and reverses the cycle in the summer, absorbing the heat inside. Thermal is the same, except it absorbs and rejects heat to the ground, which makes it more efficient because the ground has a more constant temperature than the ambient air outside. The other advantage of geothermal is that you can reject the heat inside the house to air or water, or both. This means that you can create heated water, or radiant heat. The only other way to do this has traditionally been to use a gas boiler. Using a gas boiler is becoming almost impossible in the city of Vancouver for any house over 3,500 square feet. A fossil fuel boiler will almost certainly exceed the city's 3-ton greenhouse gas emission limit. And that limit's getting smaller, by the way. What this means is that the only choice available if you still want radiant heat is to go with geothermal, which has a very high capital cost. The other option is an air-to-water heat pump. It absorbs heat from the outside air and rejects it to water. As the province goes the same directions for GHG emissions, air-to-water heat pumps will become increasingly the only option available for houses that insist on radiant floors. Market context. Here's a problem. The North American market does not have any significant demand for these types of systems. And consequently, air-to-water heat pumps haven't been on the market in North America. Vancouver, you can probably count on your fingers how many of them have been installed and operational. It means few products market tested over a period of time long enough to equal an equipment life cycle. Less product support compared to conventional HVAC equipment. Less trades qualified to competently design, install, and maintain these systems. The construction industry in general has a very poor understanding of air-to-water heat pumps. This includes architects, builders, government officials, and homeowners. Air-to-water heat pumps cost more to install compared to gas boilers. These are some of the problems. And you can see the branding of a number of the air. Many. Another issue with these products is that they are not apples to apples. But not cooling. Some will do both, but not domestic hot water. At least one of these will only do domestic hot water. Like conventional heating and cooling products, they don't match each other's efficiencies and capabilities. Another problem with air-to-water heat pumps is their cost. Quality new boiler that used to do the job for about $3,500 to $6,000. Replaced by a heat pump that does less of a job at $7,000 and go up. I believe it's very important to be clear with our clients that a heat pump is not about saving money. It may save the planet, but not money at the current price. So that might change. Here's the cost of heating for 1 hour at design conditions in the winter for a typical house, 4,000 square feet, built to an equivalent of about step 3 code in Vancouver. If you look at the top, electric baseboard at the top is a 1-to-1 ratio of energy in versus heat out. In other words, a COP of 1. Down the list, heat pumps range in efficiency, and so these numbers apply to any kind of heat pump. Geothermal tends to be at the top of the efficiency scale at about a 3.5 COP or better. Air-to-water heat pumps range between a COP of 1.59 to 2.75. Air heat pumps have a similar range with some exceptions that get very close to geothermal in their efficiencies. As this chart shows, a natural gas boiler is the least expensive to operate. Again, I gotta say that this could change. So key points on air-to-water heat pumps. Note, where there are GHG limits and radiant heat is desired, air-to-water heat pumps will have less of an upfront. Electric boilers or baseboards. As an emerging technology in a regulatory demand management, heat pumps are going to experience some growing pains. Some of those challenges will include scaling the market, trades training, generating awareness in the industry, building an acceptable value proposition. Good news is that governments, industry, and manufacturers are working on this as we speak. Finally, on the subject of air-to-water heat pumps, it's important to understand that these are complicated products in complex systems. The critical action is to ensure that you have a competent designer to make the most appropriate decisions regarding selection and design of this type of system. And if you're not sure, send the design to the specified manufacturer for a peer review. They'll be happy to help in most cases, and if they're not helpful, then get a different product. Key takeaways. Sooner or later, HVAC mechanical systems will have to conform to everyone's interest to expect better. Without proper load calculations, you're flying blind and putting your faith in coincidence. Load calculations should be performed early in the project, about the same time as the energy modeling from your EA. Check the loads and use them to explore options. Integrated design is simply coordinating, managing clients' expectations, determining the design strategy that best meets those expectations and has the least amount of impact on budget and aesthetics. New technologies are new opportunities. Whether or not it's required or desired, it's important to adapt, but with caution and qualified support.